All right, we are looking at this problem about Bart Simpson over the years. He's become pretty adept at using a slingshot. One day he pulls back his slingshot, which acts as an ideal spring. K equals 60 newtons per meter. So the spring displaces 0.3 meters. He then releases the sling so that it fires a 0.150 kilogram pebble horizontally to the right. Okay. Draw an energy graph for the slingshot pebble system with the sling being stretched at the initial position and the final position while when the pebble reaches maximum speed. Always got to read what's going on in the problem, but it looks like in the beginning, I'm looking at this, and the end is going to be right after this point when the pebble is moving very quickly to the right and has that big speed. So if I'm looking at all the energy in my system, in the beginning, I have to ask myself what types of energy I have. Now, I could have spring potential, gravitational potential, or kinetic energy. And those are my options here. Given those options, because we're not going to talk about any heat that's generated, the problem would tell us if there's any rough surfaces where that would happen. I'm only looking at these, and I say, all right, is there anything stretched or compressed in the beginning? And the answer is yes, so there is some spring potential energy. With these bar charts, as an arbitrary amount, however much you say, we can make sense of them relative to each other, but, I'll just say 1, 2, 3, 4, 5, 6 blocks of spring potential energy. Is there any height? No, because we're assuming that y equals 0 is here at the slingshot. And we're looking at right before the launch and right after the launch, so that is 0 joules of gravitational potential energy. And in the beginning, we're not moving, so there's no kinetic energy, because you need speed to get kinetic energy. Then, there's no more spring potential energy. The pebble is released, and the slingshot goes back to its equilibrium length, and we've got nothing. Still no height, because we're still right next to it at that same vertical location. So now we've got 6. 2, 3, 4, 5, 6. Wonderful. All right. Using the conservation of energy, write an equation for the slingshot pebble system that shows the initial and final states, only using the terms US, UG, and K if they're necessary. Okay. Using the conservation of energy, I can do that. Energy initial plus any work done equals the final energy. And the good news here is this is a closed system. We don't have any outside forces acting on this system while the slingshot's being shot. There's no pebble, there's no forces acting on the pebble, no forces acting on the slingshot after Bart lets go. So this is a closed system, and there are no outside forces. So work equals 0. Then, okay, how much energy is there in the beginning, or what types? Well, we already did that in the bar chart. USI equals, not U, equals K final. And that's our equation. I'll put it right here, just make it a little cleaner. Equals K final. And that's just the mathematical idea behind this. Well, now it says determine the maximum speed of the pebble as it's launched. I can do that because I can start off with this idea that we had before, that all that spring potential energy is turning into kinetic energy. Or I could say 1/2 K delta x squared equals 1/2 mv final squared. And I'll say delta x initial. And just like all of these problems, it looks like I know everything except for one of these knowns. And that's when I know I can solve this. The kinetic energy is unknown, but I know how much spring potential energy there is because I have 1/2 K becomes 60 newtons per meter. Delta x, how much are we displaced in the beginning by the spring? That's that 0.30 meters up there, squared equals 1/2 m, mass of the pebble, 0.150 kilograms, times v final squared. And now it's just math time. And that's 0.5 times 60 times 0.3 squared. gives me 2.7 joules of total energy in my system in the beginning. I'll bring this up here. And then 0.5 times 0.150. And then I'll just simplify that. That becomes 0.075. Turns out the units there are kilograms, because 1/2 doesn't have units. I'll divide 2.7 by 0.075, and I get 36 equals VF squared. And then I'll take the square root of both sides, and I get a final velocity of 6 meters per second. Mathematically, that's plus or minus 6, but all we want is the speed, so just that positive number. And then if the sling were fired straight upward, how high into the air would the pebble go? And this is great because it puts a little spin on this problem. It says, now this is not happening, being fired straight to the right. Now the slingshot is being fired straight up into the air. And that's my little slingshot, and that's my sling, and then it's going that way, and then going that way. And I could say, this is my initial, and this is my final. Now, you have different options, and I've seen different people do this different ways. But either way, they start with energy initial equals energy final. Everyone says their final point is the highest point, so we can talk about that. Because that is the point. We need that to be our final point. That is what we care about. And we're asked for how high it goes into the air. There's no spring potential energy because the slingshot is not stretched anymore. There's no kinetic energy because we're at the highest point. And that means there's only gravitational potential energy, because up at this point, the speed is 0. When you throw something straight up into the air, it stops for just a minute, just an instant while it is up there. And then in the beginning, where you set your initial point is up to you. Some people said that in the beginning, it was all kinetic energy, because it was the point after it was released. And then they did 1/2 m6 squared. And other people said the beginning was when the spring is fully stretched, when the slingshot is stretched. Either way, however you do that, you're going to end up with 2.7 joules in the beginning. And that means there's 2.7 joules at the end. Energy in the system is conserved. So then I set 2.7 joules equal to mgy. And that mass is still 0.15 kilograms. That g is still 9.8 newtons per kilogram. And then I'm left with y, and that's equal to 2.7 joules. So 2.7 divided by 0.15 divided by 9.8 gives me a height of 1.8 meters. Not the highest height in the world, but it's not the strongest spring in the world. It's 60 newtons per meter. Just like shot, poof, just a little bit up in the air. Kind of makes sense with a speed of 6 meters per second coming off of that slingshot. That is problem 1.